my great pleasure to introduce Yuansi Chen from Duke. So if you don't know, Yuansi achieved instant mathematical stardom last year by making a spectacular improvement on the status of the KLS conjecture. And today he's also going to make a spectacular improvement, but on our work, I guess. All right, it's going to talk about Mala and mixing time of Mala.
Thank you, Philip, for the nice introduction. And first of all, I would like to thank organizers for putting up this wonderful workshop with mix of like people with very diverse background. Today, I'm going to talk about minimax mixing time for Mala for log-concave sampling. This is joint work with Karu and Scott Schmidler. Karu is a PhD student co-advised by me and Scott. And Scott is colleague in our Department of Statistical Science. The paper is posted on arXiv. Okay. The talk will be three parts. First, just set up the minimax setting. I have to define what's in the mean and what's in the max. And then the second section will be to design, like to find a hard target distribution and describe how do we establish the lower bound. And then the last part will explain how do we improve the current mixing time upper bound for Mala. Okay, let's get into the setting. So the setting has been come up multiple times in this workshop. We're trying to sample from a log-concave target distribution, so e to the minus f, where f is convex. And I'll specify additional assumptions later. And we focus on one type of algorithm, just Metropolis-Adjusted Langevin algorithm. This has also been described. So it starts with some initial distribution, and iteratively, it draws samples from a proposal distribution that is just like you take a gradient step and then add some noise. And the scale of the noise is basically a square root of this step size h. And then you use a Metropolis-Hastings step to do accept reject. And this is basically to ensure that this Mala algorithm converges to the correct target distribution. Okay, so if you don't have this Metropolis-Hastings, then you have unadjusted Langevin, and you have some asymptotically your samples will be biased. Okay, so the mixing time is simple. So if we denote the t to denote the transition operator of the Markov chain, the mu n is the distribution at iteration n. Then the mixing time is the first time when the total variational distance between the mu n, the target distribution is less than epsilon. Okay. And then we try to understand this minimax mixing time in this sense. So look at this quantity. So here we have the total variational mixing time here as a function of epsilon and initial distribution. So we fix all these parameters, dimension d, the smoothness parameter L, and strongly log-concave parameter m, and epsilon m. And then the nature will choose a warm star defined in this sense that the ratio between the initial distribution and target distribution is bounded by m. And nature will choose a warm star. And then nature will choose the target distribution. The target distribution will be log-concave distributions. They are log smooth, so the Hessian of the f is bounded by L. And strongly log-concave, the Hessian is lower bounded by small m. And it lives in d-dimensional space. And what you can do as someone running the algorithm, you can choose the step size h in Mala. Okay, is this minimax setting clear? And in the following, we'll try to make some simplifications. That is still a kind of hard problem. What we'll do is that we'll focus on the dimension d and the condition number Kaba dependency. So here, I forgot to mention that the Kaba here is the condition number is basically L over m. Okay, and we will focus on to discuss this minimax mixing time. We will focus on d and Kaba, and we're gonna all polylogarithmic dependency on d Kaba and 1 over epsilon. And And we assume that basically log m, the warmness, is only logarithmic dependency on d and n kappa. And so in our setting where we ignore all this polylog dependency, this warmness is treated as a constant, and it is referred as warm star in the following. Okay. So what is our goal? We try to prove a tight upper and lower bound for minimax mixing time in this sense. So if we fix this to be a warm star m, and we want to prove this minimax mixing time, ignoring all this polylog dependency on d kappa and 1 over epsilon, this is roughly kappa d to the 1/2. Okay, that says that actually for this class of problem, if nature is allowed to choose this log-concave distribution, strongly log-concave smooth, you have to pay, like if you apply Mala, you have to pay some dimension dependency of d1/2 and have to pay the condition number dependency kappa. Okay. So of course, we are not the only one working on this upper and lower bounds for Mala. So the earlier works, those dates back to Roberts and Rosento. Says here talking about some like old work where they tried to work out this what's the correct step size for Mala, and they find that asymptotically d to the -1/3 was the correct step size scaling for product distributions with some high order regularities. And there are also many other settings in the limit of time I will not be able to talk about all of them, but yeah, there are settings people assume like very high order derivatives, try to work out the discretization error, and like especially in those Borabi, Eberle, and Harrow papers. And then in this course, we'll focus on exactly our setting, exactly this L log smooth and M strongly log-concave setting. And in this setting, we'll list some of the very recent work. And the first was DVD and all, 2019. They prove basically under warm star, the mixing time upper bound is of this form. So you have a max of two quantities, d to the 1/2, kappa to the 2/3, kappa to the 3/2, and d to the d times kappa, the max of these two quantities. So it's kind of slightly larger than ours, but it's very close. And then in our paper in 2020, we actually improve the warmness dependency a little bit. We will try to be able to prove that even if you initialize from this Gaussian distribution, and you will get similar mixing time upper bound. And then in 2020, Lee and al. Paper, they proved that from Gaussian star with variance 1 over L identity, you will have a mixing time of kappa times d, which is taking basically the second term here. And then on Tuesday, we have seen that Xingho and all and Philip and all they have shown mixing time upper bound from a warm star, which is d to the 1/2 kappa to the 3/2. It's actually taking the first term here, so it's also better. And in our paper, we try to prove so d to the 1/2 and kappa here as an upper bound from warm star. And it's worth noting that actually you can say that in this paper they already achieved d to the 1/2 kappa by combining the Tuesday talk by Xingho and the Wednesday talk by Ruoqi. There's a reduction framework that allows you to shave off all the kappa dependency, but then you have to use that algorithm which is not Mala, right? So if we focus on Mala, this will be the current story. Okay. Any questions about this? And there are also previous work on the lower bound. The lower bound problem consists of finding harder target distributions where Mala have difficulty to sample from. And actually for this like specific kind of constructions, very, very concrete constructions actually started in Chui and all 20 they were trying, they constructed a target distribution with a perturbed version of the Gaussian, which is easy to analyze, but very hard for them to sample for MALA. And they prove a spectral upper bound, spectral gap upper bound of order d to the 1/2, which usually spectral gap upper bound implies the mixing time directly, but in the continuous time continuous state Markov chains, it's not that trivial. So we will present some work trying to make this link, but actually essentially they prove this dimension dependency should be d to the 1/2. And so if we don't assume warm star, very warm star is of order log polylog d, log of warmness is polylog d, then it's hard to get d to the 1/2 dependency. In this paper, 2011 paper, they show that actually Kevin presented on Tuesday. They show that if you have initialization that is exponential to the d warm, then to get MALAs to mix, you have to take d times kappa. So you cannot get d to the 1/2. Okay, it's only possible to get d to the 1/2 when you assume a warm star. Okay.
Quick comment. I think Kevin pointed out to me that for our lower bound, like we construct a set S of like pretty high probability, such that like the conductance out of this set is exponentially small if the step size is taken too large. So if you like take as your initialization the distribution which like starts in this bad set, then it seems like it would imply a mixing time lower bound under warm start. Maybe we could discuss this afterwards, but
yeah, thanks for the comment. Yeah, we'll discuss offline. Okay.
Yeah, well, sorry. So these are lower bounds just for MALA?
Yes, just for MALA. Yeah.
Okay. So why is that interesting? I mean,
it's interesting mostly for theoretical purpose. Like for people starting MALA, you know that you cannot prove true beta rates, so you will not be able to.
But I mean, like we saw in the previous talk, there are 10 different very interesting algorithms, right?
I agree. I totally agree. I think this lower bound, does not hold for other algorithms. For HMC, for example, already doesn't hold. Yeah.
Do you expect it holds if you restrict to gradients only, gradient computations only?
Yeah, it's hard to say. It's one of the conjectures like Xinghe was trying to impose in the open problem session that it's difficult to get. So we only be able to get very like specific to MALA, and these are the kind of the lower bounds. Okay. Thanks.
No.
Okay, let's first talk about the lower bound, which is has a lot of tedious calculation, but in presentation it might be easier. So yeah, so the lower bound sketch here is used in many places. So we just consider one algorithm, so it's not that hard to establish lower bound. So we first find a hard target distribution, and then we try to prove its spectral gap is small, and then we try to get a mixing time lower bound from spectral gap upper bound. Okay. The first part is largely inspired by previous work, Li et al. And Chui, this construction. They basically in Li et al. 20, they got for Gaussian distribution, they got the kappa dependency tight, and Chui et al. They got the d dimension dependency tight. And yeah, so we were at that time, like when Xinghe published their paper or like posted paper on arXiv, we were working on some similar problems, but a similar kind of construction, but we find, their construction is actually much better than ours. It's easier to analyze, so we can adopt this kind of construction. So if you look at this construction of f, so the target distribution will be e to the minus f, right? This construction of f has kind of two types of components. You basically has the Gaussian part of the quadratic part, and you have a perturbed part is like these cosine functions. And what's the intuition here is like for the first d minus 1 dimension, you have a perturbed Gaussian part. And why is this type of perturbation? You can try to take the second derivative of this quantity. The the second derivative and look at Hessian, you will see that the Hessian actually oscillates between 1/2 and 3/2L. L is smoothness parameter. And the oscillation is very fast because it's like D is inside this bracket. When you take second derivative, it will be like some constant minus some cosine D to the 1/4 X. And this oscillation very fast basically will make the malar, like you have to take a small step size in malar to be able to achieve a small accept reject rate, and this will give you the correct dimension dependency. And yeah, the construction in Chewy null was very kind of smart, and I recommend take a look at this. And then you look at this last dimension. You just need actually one dimension that is does not have the same scaling than the other dimensions. This make up here this small m, and this part makes which is much smaller than the L, and this difference is enough to make up here the kappa dependency in the mixing rate.
Can I ask, why is it 1/√D in front of the perturbation term?
Yeah, so that's a good question. So we want the oscillation to be fast here in the cosine term. So we want to put some D here. And then at the same time, you need to ensure it is log-concave. So when you take second derivative, this term is always positive. So you have a constant term 1 of order 1 minus the derivative, second derivative, you will have like D to the 1/4 coming out 2 times, and this D dimension dependency cancel out will be like constant minus cosine. And this is basically to make sure that it's roughly constant minus cosine. Otherwise, yeah.
I see. So the perturbed Gaussian is essentially to introduce some oscillations of the gradient.
Yeah, oscillation of the Hessian. Yeah, that will also imply the oscillation of gradient. But it's yeah, because of this kind of scaling, it's interesting that you see that if all the axes actually concentrate around square root D radius, this does not have much effect actually, because this is quite small. But when X is like inside this square root D radius, this starts to have like large effect. Yeah, so the second step is trying to bounce spectral gap of this target distribution. I will not present it here in the limit of time. It's feasible because like we know it's feasible, but it's just tedious math because it's a product distribution. It's a perturbed version of Gaussian, and you can have all the derivative of this function explicit. So then the third step is trying to get mixing time from spectral gap. This is well known in actually in finite space sampling. And for example, you can take a look at this very well written review in Montenegro and Tetali 2006. So somehow for the continuous space mixing, I don't know if people maybe people don't care about this kind of rate. We cannot find an explicit theorem that relates the mixing time and spectral gap, but we have to dig a little bit into the literature that there exist the tools. So this theorem is not hard to prove. That we dig into literature and find the correct theorems, and we prove something like the mixing time is lower bounded by spectral gap of some initialization mu0. And because of this inequality, you can construct your mu0, bound your spectral gap, and you get a lower bound for mixing time. Okay. Yeah. So we cannot find an explicit theorem like this for general state space or continuous state space Markov chains. If you know something in the audience, please let us know. Okay, let's get into the upper bound. The upper bound is interesting. There have been many attempts, and I'll try to show you the refinement in our proof. But before that, let's go through the general proof sketch that has appeared multiple times. So we use conductance-based mixing time proof. This is not the only way to prove mixing time, but it's the way that we use and it works well. At least I know very well this proof technique. So this was first developed very well in the finite space macro chains. And it actually became very popular since Lovász and Simonovic 1993 paper. They made this theorem, a series of lemma that made this type of proof very easy for continuous space safe macro chains. And the typical strategy is like three steps. So you first show that the conductance will give you a mixing time. And then to get the conductance, which is the notion that is very difficult, like you have to control all the quantity over all subsets. There's a way, like, is it sufficient to consider some kind of local properties with what we call transition overlap to get conductance? I'll explain this in details. And then the third step to get this local properties transition overlap, we'll use some, it's sufficient to show the proposal overlap and some control of the accept reject rate. Don't worry if you don't get this, but I'll explain this. So the first step is to relate the conductance and the mixing time. And the conductance is this quantity. So you have a transition kernel at point X, and you look at the mass, how much mass you can transfer from one subset A to its complement. So the picture to draw is like this. You have a set, you have some distribution, and then you have a subset A and A complement. You try to look at how much mass you can transport from one side to the other. Of course, if your like distribution behaves well, you expect this quantity to be large. And if distribution have some kind of bottleneck, then it's hard to transport mass from this A and A's complement here, and then your conductance will be slow, and then your mixing will be small, and your mixing time will be like large, okay? And so this Lovász and Simonovic 1993 paper show that this conductance lower bound implies mixing upper bound. The total variational mixing time is roughly 1/5 squared. This is under warm star, and we ignore all the other log factors. Okay. And there's some kind of improvement of this technique in their paper, that in some cases you really don't want to bound the mass kind of transfer for certain very small measure sets. And this S conductance serves this purpose, that you don't actually need to consider all subsets A with very small masses, and you can ignore them and define this S conductance. S conductance also gives you a mixing upper bound as long as you choose S to be not too large. Okay. And the second step is also kind of interesting proof technique, and overlap is because this conductance or S conductance is something seems like very difficult to bound. You have to go through all the subsets A, like from size S to 1/2, and like for a convex set, you have many ways to draw these subsets, right? So directly bounding this quantity is difficult. And in this Lovász 99 paper, they try to say that, oh, you don't need to bound this conductance like from its definition. There's a way to bound it through local calculations. Local calculation means that you just need to consider any 2 points that is some radius r apart. And as long as you can prove this, if they are radius r apart, their overlap, the total variation distance between their transition distributions have a large overlap, then you get a mixing time, you get a conductance lower bound. So it's like you have any point X and Y, and the proposal distribution might be some kind of Gaussian shaped around them. And then as long as you can prove that if for any 2 point X, Y, they are close in distance R, they are at overlap between the Gaussian proposals, they this overlap is large, TV distance is small. And then you can prove conductance lower bound like this. And what up here on the right side, you have the isoperimetric coefficient and the radius r. So I think like Santosh just explained to us as well, it's this kind of genius kind of proof strategy that you want to prove something about Markov chain, but you end up using the isoperimetric coefficient, which is the intrinsic property of the density you want to sample from. Okay, and for strongly log-concave densities, this is of order square root of n. And the similar lemma holds for the S conductance. We will not describe it. That gives some convenience because you don't need to. Sorry, here's the typo. You don't need to consider all x and y. You just need to consider x, y in some high probability set. So because we use this type of strategy, our upper bound proof actually it does not need this strongly log-concave assumption necessary. As long as it is log-concave and smooth and have some kind of isoperimetric coefficient, we will prove upper bound for Mala. And usually you can get the isoperimetric coefficient without this strongly log-concave setting. For example, if you know the target density have some bounded variance, and then you can make use of the theorems related to the KLS conjecture to get the isoperimetric coefficient. Okay. So the last step is trying to bound this total variational distance. So this transition, this is what we call transition overlap. So it's the TV distance between this transition distribution at x and at y. And the typical way it works is to use the triangular inequality because we know this Qx is a proposal distribution. The proposal distribution is just a Gaussian distribution. So we know this proposal distribution much better than this transition distribution. And make use the triangular inequality allow us to isolate this proposal overlap, and then everything boils down to control this accept reject rate here. Okay. So yeah, so this middle step is easy because we use Pinsker inequality and KL divergence between Gaussian is easy. And we have this accept reject rate to control. And let's look at this accept reject rate here. We need to bound this total variational distance between the transition distribution and proposal distribution for any x that is sampled from target distribution with high probability. So this quantity will be like 1 minus expected accept reject rate. So you basically have like two type of randomness. One is like you only need to bound this quantity for x from target with high probability. The other is you have expectation over y, which is like the noise distribution when you generate a proposal. Okay, you want bound this term in high probability, and so you want to control this accept reject rate in Mala. There have been many attempts, especially with Ras DVD, and what we did in the PhD, like we tried to bound this term because like we thought this is kind of easy to bound and just use some kind of Taylor expansion and triangular inequalities. We not be able to get. Remember, we only get like d to the some max of two quantities like d kappa and d to the 2/3 kappa. So roughly d kappa. It's not the best rate we get, but so here the takeaway here that if you don't make use of these two kind of randomness in y and randomness in x very well, you will not get a very good accept reject control. And also, so Lee and all 20 paper, they already have a better use of the randomness on x, because see, if you know x is coming from log-concave distribution, you have a better way to bound the gradient of something that is drawn from log-concave distribution. That's what they call the better gradient concentration for log-concave distributions. And there they improve, yeah, instead of our like max of 2 quantities, they get like just d kappa, which is better than ours. And single tree and all, they take a different approach. Instead of considering this, just looking at this triangular inequality, they said, oh, people know the Langevin division much better than this discretized, this malar, and let's explore some properties of Langevin distribution to get a better estimate of this accept reject rate. Okay, and we are kind of old school trying to bound this quantity. So this quantity, according to tree and all proof, has to be bounded very good. But yeah, let's try to expand these terms and see like really what are terms we cannot bound and what are terms we can bound, and to see like what's the difficulty. So we have to make one connection to bound this accept reject rate to see this malar as a Hamiltonian Monte Carlo with one step of leapfrog integrator. So this has been introduced many times. Let's go through it quickly. You have this Hamiltonian function. This is the fq plus square 1/2 p squared. And then from the continuous dynamics, just satisfy this 2 differential equations. And then if you discretize this differential equation, you get what we call Hamiltonian Monte Carlo, the discretized version. And if you discretize it with the leapfrog integrator, then you get this type of updates. And the updates for Q, if you stare at it, it will look very similar to the malar update. So the update on Q will be Q0 plus eta P0 minus eta square over 2 gradient of FQ0. So if you think this, you identify this Q0 is the initial state X, P0 is the noise you add when you propose, and this is exactly X minus some gradient term plus some noise term, and the step size exactly match if you think H is eta square over 2. Okay, so this is a connection, and this actually makes our analysis easier because now we can also make use of this a lot of things proved for Hamiltonian Monte Carlo. So the malar accept reject rate in the PQ notation, it just becomes this. Remember in the XY notation is this, but from this to the PQ notation is just the transform of those variables, nothing else. And then we make use that the continuous Hamiltonian Monte Carlo dynamics conserves the Hamiltonian. So at any time t, FQT plus the 1/2 PT squared is equal to FQ0 plus 1/2 P0 squared. And then we can basically replace this term, with this term. So after replacing this term, we get this term, right? So at time, so this will be the continuous dynamic at time eta. This will be the leapfrog integration of this Hamiltonian dynamic at time eta. So the malar accept reject rate is just the running HMC for one step with the leapfrog integrator and look at the discretization error on the Hamiltonian. So everything boils down to control this HMC discretization error. So let's say how we bounded this discretization error on the Hamiltonian. This is our kind of key lemma, which is new in our proof. You can try to bound this quantity like by like triangular inequalities, and there are some term left, and we ended up bounding it like this. And the second part is basically from triangular inequalities and gradient concentration, and the first part is our kind of new part. And from here you can see to make this accept reject rate to be about constant order, then the step size eta square will be take 1 over square root d, and h is of order of eta. So h is of order of eta 1 over square root d, and I forgot to explain the conductance will be just roughly 1 over mh, and the mixing time will be time be 1 over c squared, then it's roughly 1 over square root. Sorry, sir. Yeah.
When you write c equals, I think it should not be
yeah, the mixing time, I think, yeah, sorry. I did too fast, but yeah, the mixing time, let's quickly go through this. So you have the isoperimetric coefficient phi square root of m. This r will be of order square root h. Okay, so the conductance will be square root h square root m. Sorry. And mixing 1 over c square m times h. No, 1 over mh, right? So it's roughly kappa times d to the 1/2. Okay, this is a calculation. So you need to make appear like basically the discretization error that has like either eta to the 4th d or eta to the 1/2 d/2. And if you just use triangle and inequality, things like that, this term will not be bounded with this order of d dependency. And the interesting thing that I want to show it's kind of complicated. If after you have done all these triangle inequalities and gradient concentration, the term that is kind of magically left is this type of term, what we call a b eta here. It's a complicated term, but it's an interesting term that that can like magically you can bound this term in high probability. What does it roughly means? It's like you have this gradient of f at q at s. This is roughly p at s, roughly some discretization of p of s. And you have the term at this 2n at time 0 and the time at time eta. This is t equals 0, t equals to eta. And then you want to bound this term, upper bound this term. It looks like you can bound this term using some kind of convexity argument. You have term on the 2n and things in the middle. Actually, this proof does not use any of these convexity arguments and is simply based on some kind of a lot of change of variables, a gradient concentration, and Herb's argument. I will not go through this. Okay, so with this proof, we will be able to prove this d to the 1/2 kappa kind of dependence, mixing time kappa dependency. So we also did some mixing time like simulations. So we consider the hard distribution that appeared in the lower bound proof. And then we try to choose the step size with different d to the gamma exponent. And we also try like either warm star or exponential d star that appeared in TNL Lee and al. Paper that Kevin presented on Tuesday, and see actually what's the right gamma actually leads to the correct accept reject rate or the correct kind of mixing time. And the mixing time, we don't have the exact handle. We have to use some kind of proxy that is the hitting time when the error in quantile, 90% quantile is small. Okay. And let's look at this plot for the top left plot first. Here we show the accept reject rate as a function of dimension. When you increase the dimension and you change the gamma parameter, and what we expect is when this gamma is about 0.5, it's shown in this solid line. This should achieve some kind of constant accept reject rate. That's what our proof trying to establish. And if you choose a too large step size, your accept reject rate should decrease to 0. If you choose a too small step size, then the accept reject rate will go to 1. Okay, so you want to keep the accept reject about constant. and also keep the large step size because you those kind of both matters for your mixing time. And you can show that if you choose a gamma that is different to 0.5, it goes down. It's interesting that in simulation, it goes down very slowly. And we were at like 10 to the 7, and it's still not at 0 yet. So it's kind of interesting. In practice, you might be able to show that you might be able to use the slightly larger step size, unless your dimension is of order 10 to the 7 or something. And on the right plot, we show the mixing time. You can show the proxy for mixing time as a function dimension. The proxy for mixing time, you can see that the solid line with the gamma equals to 0.5 exponent has the lowest kind of mixing time, proxy mixing time. We show something for the similar things for bad star, where the bad star appeared in this Kevin's talk, and you can see that for bad star, you really need to take gamma d to the -1/2 like small step size. Otherwise, your step reject will drop very fast to 0. Okay, and that's this kind of different situation. So it's hard to get d to the 1/2 dependency if you really have a bad star. Okay, let's summarize. So we established the minimax mixing time formula for log-concave sampling from a warm star, which is d to the 1/2 kappa. For people like trying to implement, so we can really try to give some kind of interesting advice that if you have moderate dimension is very small, then you really don't care about the dimension dependency. You might be able to choose a step as 1/L, like people choose for optimization. But if you really consider this log-concave sampling, and you don't know much other than it's just log-concave, and dimension is large, you should choose 1/d to the 1/2 step size. It might be okay, like in this Roberts and Rosento paper, it might be okay to choose the largest step size if you believe the target distribution is like Gaussian-like and has high order regularities. But if your initialization is really bad, like Kevin showed, that you need to choose a very small step size 1/d formula. Okay, and some open directions, some of them already appeared yesterday, that you want to remove the requirement of warm star, you want to have adapt step choice for Malar, and you want to also show something similar for Hamiltonian Monte Carlo. And that's the end of my talk. Thank you.
Any questions?
Maybe I'll ask one. So it's kind of interesting that you actually compare the Mala with HMC discretization. So I guess naturally one would curious about what if you do a Metropolis-adjusted underdamped Langevin sampling. Have you thought about that?
That's an interesting question. I'm not an expert on this, but I heard that if you just use HMC on Metropolis adjustment for underdamped, you don't get as good as dimension dependency for mixing when you compare it to the unadjusted version, but I'm not very sure.
Thanks.
Other questions?
Can you extend this result to k-step HMC?
Yeah, that's what we were trying to do. And yeah, we can discuss after this. Yeah, it's not easy. So somehow I think we lack some understanding of this quantity. And yeah, there are experts on Hamilton dynamics and continuous dynamics here in the audience. I will be happy to discuss if you can tell me what's actually the meaning of this type of quantity. Why does it magically? It's actually very small discretization error for this type of quantities, and that will help also for understanding, like for Hamiltonian Monte Carlo, why can the current proof cannot get a good accept reject rate, and how to improve.
In your open directions, you mentioned like developing new proof techniques beyond S conductance. In light of your lower bound, what exactly like do you hope to accomplish with this development?
Yeah, I don't know. Currently, we're kind of stuck at this kind of S conductance proof. But if you look at discrete sampling literature, you have all these kind of proofs that does not based on the conductance, and they get better dependency on the warmness. And we were looking at it, and currently we don't know, but it's kind of one thing we are learning still. Yeah.
Can you rule out a log sub law of inequality?
Sorry, it's basically for the warmness dependency. It's not the log sub inequality. It's basically log m kind of dependency. Yeah. For strongly log concave distributions. Yeah.
Right. So the S conductance forces you to use a warm start.
Yeah. So you only have to get log m dependency if you use the S conductance argument in our proof. Yes.
If you had a log sub law of inequality, you could hope for a log-log.
Yes.
So
but we kind of expected that even if you don't explicitly assume the log sub of inequality, deal with the strongly log concave distributions, you should also get log m. That's somehow in a lot of simulations we don't really see this warmness dependency. And that's kind of intriguing. Yeah. If someone can construct also lower bound case, like worst case examples where you have to pay this warmness dependency, that is also interesting. Yeah.
Doesn't your lower bound, for instance, like rule out the possibility of getting this log m dependence?
Yeah. So yeah, but we don't know if there are lower bounds like that, right?
So like, do you mean like developing proof techniques that use the initialization beyond just the warmness parameter? Because that seems like the only way to really get around your lower bound.
Develop proof techniques where only has log m kind of dependency. Yeah.
But like if the only thing that your proof uses is the warmness at initialization, then your lower bound would, like the lower bound, I guess like I'm talking about Kevin's lower bound here, like that would rule out the possibility of log m dependence with d to the 1/2, right?
I'm not sure, but yeah, I have to think about it. Yeah, let's discuss after. Yeah.
All right, so since it's time for lunch, I suggest we all thank Yuansi and all the speakers of this morning. And we'll meet again at 2. Enjoy your lunch.